Hello, I'm Clyde Witchard, a systems engineer at Picocom working on digital pre-distortion. Today I'm going to be talking about our DPD solution that we've developed for 5G NR sub-6 GHz small cell base stations. Our algorithm development environment uses MATLAB to execute a model of the DPD algorithms, and the MATLAB model interfaces to a real power amplifier using Rohde & Schwarz RF test equipment to linearize the downlink path. Today I'll be demonstrating how this system linearizes an Icana 4-watt gas power amplifier in an FR1 band. Okay, I'll play a couple of introductory slides now, then we'll come back to the lab and put the hardware through its paces.
This diagram shows the Small Cell Forum's reference design for standardizing components and interfaces within a 5G FR1 small cell distributed radio unit. DPD is usually the final major digital signal processing block in the transmit digital baseband chain. For that reason, within this standardized partitioning, it's appealing to integrate DPD in the baseband system toward the end of the PHY, shown as option 1 here. Another option is to place DPD within the RF transceiver system toward the front of the baseband processing in the RFIC, shown here as option 2. Here at Picocom, to support efficient and comprehensive development, test and optimization of our DPD algorithms, we've adopted a hardware-in-the-loop approach. The elements of the system are shown here. Our DPD algorithms are developed and run in MATLAB on a PC. The PC is network connected to Rohde & Schwarz RF test equipment, communicating via SEPI commands with MATLAB. We have a vector signal generator that takes transmit baseband IQ samples from the MATLAB model and replays and upconverts it to RF. The generator's RF output is connected to the input of the target PA undergoing linearization. The output of the PA feeds through a power attenuator to the RF input of a signal and spectrum analyzer. The analyzer down converts the signal, captures it as IQ data, and sends the data back to the MATLAB model. The captured data acts as the DPD observation channel to train the DPD algorithms running in MATLAB. The analyzer also performs live spectrum analysis, giving calibrated measures of power, ACLR, and other useful measures.
Okay, now let's run the hardware-in-the-loop system we just saw in the last slide. I'll show the performance at the output of the PA with no DPD applied, then we'll run the DPD, let it train and correct the signal, and then look at the performance again. First, let's talk through the specific hardware we have here. Starting at the back of the transmit chain, we have an Icana 4-watt PA. It's the ARQ SP3437, operating between 3.4 and 3.7 GHz. The PA input is provided by the Rohde & Schwarz VSG, which is providing 100 MHz 5G NR signal centered at 3.55 GHz. And as we discussed on the slide, the signal baseband IQ data is provided by the MATLAB DPD model. The PA output feeds through a power attenuator to the Rohde & Schwarz FSW, which acts as the DPD observation channel, sending the IQ data back to the DPD model. Okay, now let's switch on the RF. The signal provided to the PA right now has CFR applied but no DPD. As we can see, the signal output power is measuring around 28 dBm, and the ACLR is measuring around minus 29 dB, with no DPD applied. Okay, let's run the DPD. A hardware DPD implementation will converge quickly in real time, but because our system here is running in MATLAB and it's running a detailed model, the MATLAB here takes a couple of minutes to converge. So we'll come back in a moment and see how it's doing. Okay, the DPD should now have converged. Let's have a look at the performance. We can see that the ACLR has dropped to around minus 49 dBs, and the MATLAB has measured the EVM at less than 2.5%. So we have a margin over 3GPP compliance with the implementation. Thank you very much.